So thank you for the introduction. So today we'll talk about PHom-GeM, persistent homology for generative models. By generative models, we mean either autoencoders or generative adversarial networks, or also known as GANs. Here is the outline of the presentation. So first I will introduce the context and also the research question. Then I will explain the methodology. So first the persistent homology concept, and then how we apply that to GANs and autoencoders. Finally, I will present some results and I will conclude. So let's move on to the context. So generative models, GANs and autoencoders, usually in research or sometimes also in computer vision, or when we try to use them, and we use them for image-based application. So for instance, here you have some faces which were artificially generated by GANs. And you can see that some faces look really real, some others are a bit strange. And this is very nice because you can automatically compare and visually compare how your sample's quality is, and you can say, okay, I need to further improve the training or tweak the models. However, what can we do when we don't have an image-based applications? So for instance, in finance or in transport, where you have like only numerical-based application. You can rely on traditional distance measures. So for instance, the parallel distance, inception distance, even the fresh inception distance. They give you a number on how accurate your training is. But usually, if you change the data sets, you can have different numbers, and it's very hard to intuitively know what does that mean. Because sometimes you have a very large number, and you have good results. Sometimes you have very small numbers, very small error numbers, and the sample's quality is very bad. And persistent homology is a field of mathematics who is specifically designed to describe data points cloud. So very numerical application, and you can visualize your data points cloud. So this brings the research question on how can we rely and apply persistent homology to generative models to assess the quality of adversarial samples in a real-world and non-image-based application. So we will describe persistent homology for generative models. We will also introduce a bottleneck distance, which is a distance measure of persistent homology. And we will apply our technique on a real-world application on credit card transaction. Let's explain a bit what persistent homology is. So I will introduce some few concepts before describing how we apply that to GAN and autoencoders. So persistent homology is a field of mathematics to describe the shape of the data points cloud. And we used features such as connected components, loops or cavities. So if you look at the bottom of the screen, on the far left you have a connected component. So it's 2 points connected with a line. In the middle you have a circle, and on the far right you have a sphere. And each of these features belongs to a different homological group. H0, H1, and H2. And what's nice about that is that it's completely free of any distance measurement. So in persistent homology, if you consider a glass, for instance, it has the same properties as a plate. Why? Because if you compress a glass, you obtain a plate. Another key concept of persistent homology is that we rely on simplicial complex. So a simplicial complex is a collection of simplex. And a simplex is just a trick to describe your data point clouds and how you can discretize your data point cloud. So you have different simplex. Here you have the 0 simplex, which is a point. Then you have a line, a 1 simplex, also a connected component. It's the same thing. And then you have the 2 simplex, triangle, 3 simplex, tetrahedron, and so on. And here is the core of persistent homology. So in persistent homology, you start with your data point cloud. And then on this data point cloud, you apply a filtration parameter called epsilon. So you artificially increase the size of each of your points. And you get disks. And then when you have disks that touch each other, intersect, then you draw a line between the connected components. And you create one simplex. And then you keep increasing the size of the disk to obtain triangles. And it helps to describe your data point cloud. You highlight persistent homological features of your data point cloud. Following the filtration parameter, usually what it does is that we computed barcodes. However, barcodes is not very intuitive to know what it is. So here we highlight first the barcode on a simple case where you have a non-monotonic function. The barcode is to highlight the birth death cycle within your data point cloud. So if we consider the case of a non-monotonic function, for every local minima, you have a birth event. You create a barcode. And for every local maxima, you have a death event. So it's the end of the barcode. Why is this useful? Is because you can then transpose your data point clouds to a visualization using only barcodes. So then the visualization becomes very intuitive and relies only on the persistent homology features. And the barcodes can also be presented as a persistence diagram. So, and with the persistence diagram, we can then use persistent homological distance measures, such as the bottleneck distance. So here you have a glimpse of, we can build a visualization technique, and based on this visualization technique for non-image based application, you can also have distance measure. So here is all the concept we talk about. You have the homological group, the barcodes, and the data point cloud. So the data point cloud is nanoless. In mathematics, is similar to a donut in real life, the thing that you might eat in the morning. And so you can see that we increase the size of each data point using the filtration parameter. And while you increase the size of the filtration parameters, you highlight some components. H0 is for the connected components, so you just draw lines between the points. H1, you highlight the loops, or the holes within your data points. And H2 is for the cavities. So if you take a donut, you can imagine it's an empty donut. So in the middle, it's empty. So this is why you just have one barcode in H2. So here you get a visualization of your data points according to different specificities of your data points. But how can we apply that for GAN and autoencoders? So in a GAN, you have usually a generator and discriminator. The generator is in charge of generating adversarial samples. The discriminator in charge of discriminating between fake and real samples. So here we train the GANs usually as it's done with a distance measure, inception distance or root mean square error. And when we finished, we generate artificial samples. And we map these artificial samples directly to a filter simplicial complex. So we map them to the persistent homology. And then using that, we can create a barcode visualization for the generated adversarial samples. And we do the same for the original data points. So we get two barcodes visualization, one for the original datasets, one for the generated datasets. And you can compare visually the differences between these two datasets, which are non-image based applications. So you get a visualization of pure numeric datasets using persistent homology. And for autoencoders, how can we do it? First we train the autoencoder, and then we map the original dataset to a barcode visualization, and we do the same. We generate artificial samples using the decoder, and we map the decoded samples to the barcode visualization. So you get two visualizations, one for the original data points and one for the generated data points, and you can compare them. So we used pure numeric datasets, which is the credit card transaction dataset of the ULB machine learning group. So the dataset is available on Kaggle at the following address. So the dataset has been anonymized. You have 2 days of credit card transaction and 29 features, including the amount. And here are some results using GANs. So you can see that we create a visualization of the credit card transaction using persistent homology. So the black wave represents the connected components, the homology group H0, and the red one represents the loops. And so we generated artificial samples using the gradient penalty Wasserstein GAN and also the Wasserstein GAN. And you can see that it looks quite close, the results look quite close. However, the gradient penalty Wasserstein GAN has more density on the right. And then we did the same with autoencoders. And here you can see that even though you might obtain a very small error at the end of the training, the generated samples are quite different. You can see that the spectrum, the red spectrum and even the black spectrum are far different from the original one. So here we created a visualization using persistent homology on a pure numeric dataset. So here you have an overview of the visual results. So in our configuration for our datasets, we were able to obtain best results with the GAN, and especially with the gradient penalty Wasserstein GAN. We were not able to get very good artificial samples using autoencoders. And using persistent homology, you can also have a distance measure, the bottleneck distance. So it's a way of comparing the similarities between the barcodes. And here it's what we did. So we compared the similarities between the barcodes of the original samples and each of the generative models. And you can see that it confirms what we observed visually, namely that the gradient penalty Wasserstein GAN was producing the best adversarial samples given our configuration. So to summarize, we introduced persistent homology for generative models. It helps to highlight the manifold features of your data points, and you can create visual tools even for pure numeric datasets. And experiments were performed on the credit card transaction dataset. And given our configuration, our dataset, we were able to produce the best adversarial samples using GANs, both qualitatively and quantitatively. So for future work, we would like to assess the influence of the homotopy type in the results. The homotopy type is how you grow the filtration parameter epsilon. And we would also like to integrate a topological optimization function as a regularizer term within the generative models. Thank you very much. I will be pleased to answer any question you may have.